There is a fascinating class of metals and compounds known as superconductors, materials that exhibit a distinct and remarkable behavior regarding electrical conductivity. Unlike standard conductors, whose resistance gradually decreases as temperature lowers, a superconductor's electrical resistance decreases to an absolute zero when the material is cooled below a specific threshold known as the critical temperature, denoted as T subscript C. This phenomenon was historically discovered in 1911 by the Dutch physicist Heike Kamerlingh Ons. While working with mercury, he observed that as the temperature dropped below 4.2 Kelvin, the resistivity did not just lower. It vanished completely. Measurements have shown that the resistivities of these materials below their critical temperature are less than 4 times 10 to the power of negative 25 ohm meters. To visualize this, that value is approximately 10 to the power of 17 times smaller than the resistivity of copper. This means that if you started a current flowing in a superconducting loop, it would theoretically flow forever without a power source. As the resistance is effectively zero, it is crucial to understand that this critical temperature varies significantly between different materials. For instance, simple metals like zinc become superconducting at very low temperatures, around 0.88 Kelvin, aluminum at 1.19 Kelvin, and lead at 7.18 Kelvin. More complex compounds, such as niobium tin, have higher critical temperatures, reaching 18.05 Kelvin. A major breakthrough occurred with the identification of ceramic high-temperature superconductors, such as mercury-based copper oxides, which can reach critical temperatures as high as 134 Kelvin. This is significant because it allows the use of liquid nitrogen, which boils at 77 Kelvin, as a coolant instead of the more expensive liquid helium. The value of T subscript C is highly sensitive to factors including chemical composition, external pressure, and molecular structure. Interestingly, the metals we typically consider the best conductors at room temperature, copper, silver, and gold, do not exhibit superconductivity at all. A defining visual characteristic of this state is the Meissner effect, often demonstrated by a permanent magnet levitating above a superconductor cooled by liquid nitrogen. This happens because the superconductor effectively expels magnetic fields from its interior. This property allows for the creation of superconducting magnets, which are capable of generating magnetic fields 10 times greater than the best normal electromagnets. These are currently essential in medical technologies, specifically in magnetic resonance imaging, or MRI units, which produce high-quality images of internal organs without exposing patients to harmful radiation. Moving to the realm of modern physics, we encounter the introduction to quantum mechanics. By the start of the 20th century, physicists realized that Newtonian mechanics and classical theories were insufficient to explain the behavior of matter at the atomic scale or at velocities approaching the speed of light. A central problem that highlighted this failure was black body radiation. In physics, a black body is defined as an ideal system that absorbs all radiation incident upon it. A common model for this is a cavity with a small hole. Radiation enters and is absorbed by the walls, making the hole appear perfectly black. When heated, this body emits electromagnetic radiation in a continuous distribution of wavelengths, but classical physics could not accurately predict the shape of this distribution. To analyze this mathematically, we look at 3 critical laws. The first is Stefan's law, which describes the total power radiated. It states that the total power P is proportional to the 4th power of the absolute temperature. The equation is read as P equals sigma times A times E times T to the power of 4. In this equation, P is power in watts, A is the surface area, E is the emissivity of the surface, and sigma is the Stefan-Boltzmann constant, equal to 5.67 times 10 to the power of negative 8 watts per meter squared Kelvin to the 4th power. This law tells us that a small increase in temperature results in a massive increase in emitted energy. The second key relationship is Wien's displacement law. As an object gets hotter, not only does it emit more energy, but the peak of its wavelength distribution shifts towards shorter wavelengths. Mathematically, this is expressed as lambda max times T equals 2.898 times 10 to the power of negative 3 meter Kelvin. This inverse relationship explains why a heating element shifts from a dull red glow to a bright white heat as its temperature rises. The peak wavelength is moving from the infrared into the visible spectrum. The third area is where classical physics collapsed. The classical attempt to explain the black body spectrum was known as the Rayleigh-Jeans law. The formula proposed that intensity, I of lambda and T, was equal to 2 pi times the speed of light c, times the Boltzmann constant k sub b, times temperature T divided by lambda to the power of 4. While this equation matched experimental data at long wavelengths, it failed catastrophically at short wavelengths. Because lambda is in the denominator, as the wavelength approaches 0, the predicted intensity approaches infinity. This impossible result was termed the ultraviolet catastrophe and proved that a new theory was needed. This led to the development of quantum mechanics and the concept of the dual nature of light. We observe that light behaves as a wave in phenomena like interference and diffraction, yet it behaves as a particle in phenomena like the photoelectric effect and the Compton effect. In the Compton effect, high-frequency radiation like X-rays is scattered by loosely bound electrons. The scattered radiation has a longer wavelength than the incident radiation, proving that the photon transferred energy and momentum to the electron just like a particle collision. Louis de Broglie extended this duality to matter, hypothesizing that if light can act like a particle, then particles like electrons can act like waves. He famously stated that nature loves symmetry. This was later proven when beams of electrons were observed to diffract, a property unique to waves. Finally, we must consider Heisenberg's uncertainty principle, which established a fundamental limit to measurement. It states that in microscopic systems, it is impossible to simultaneously measure specific pairs of physical quantities, such as position and momentum, with absolute accuracy. If the measurement of one is certain, the other becomes inherently uncertain, defining the probabilistic nature of the quantum world.